Kia koto koto. Welcome back to another exciting AP Chemistry video. Now, today our focus is going to continue on what we talked about previously on chemical equilibrium, but what we are going to discover is the concept of the Rice table. This is a way that we can go through and figure out a variety of different variables for situations where equilibrium occurs. So make sure we pay close attention because that is something that is going to reappear more often than not over the next couple of units. In addition to that, we are going to start diving into Le Chatelier's principle in order to understand how we can make changes to a system at equilibrium to shift chemical equilibrium to favor the creation of more reactants or the creation of more product. So stay tuned for another exciting video. So here are our student learning objectives. Hopefully you'll be able to calculate the pressure and concentration based on experimental values and the value for K. We should be able to use particle diagrams to represent relative numbers of reactants and products at equilibrium. Describe what happens when external stress causes Q to no longer equal K. Use Le Chatelier's principle to describe equilibrium shifts in a chemical reaction. Know what factors do not cause shifts in equilibrium. Be able to explain that an external stress may cause Q to no longer equal K, which results in the system reestablishing equilibrium. That's when we're going to look at Le Chatelier's principle. And then describe how changes in temperature impact the value for K based on whether the reaction is endo or exothermic. So when we calculate equilibrium concentrations, knowing the value for K and our initial concentrations, we can calculate equilibrium concentrations by making a Rice table. Now, when making a Rice table, we need to make sure that we understand what those four letters in Rice represent. And they represent your reaction, your initial conditions, what changes, and then based on the initial and what changes, what variables are we going to get at equilibrium to calculate whatever variables we are looking for. So a few things to keep in mind as we go through and complete these types of problems, but you'll see it once we do a practice problem ourselves. So let's take a look at this equilibrium situation. It says find the equilibrium concentrations for HA, H, and A. So this really is an acid-base problem because we're looking at an acid, some acid HA, and it dissociates into H and A minus. However, we know that the system is at equilibrium for two reasons. First off, it gives us a K value. And secondly, we have our double arrow. So we need to figure out what these equilibrium concentrations are. So again, we have our initial concentration of acid, which is 0.30 molar. So that is our reaction, okay? We're given our reaction, and we're also given our initial conditions. Our initial conditions are that we have 0.30 molar HA, and because the system has not established equilibrium yet, all we have is reactant. We don't have any product yet. That's going to be based on the value for K, and you'll see that in just a second. Now, our change, we don't know. We don't know how much of HA is going to dissociate into H plus and A minus. So what we do is we say that we don't know that value, so we're going to call it X. So as a result of this, we're going to subtract X from our reactant side because X is going to be how many products we make. And because everything's in a 1-to-1 mole ratio, we're going to add X of H, and we're going to add X to A. So if we think about this logically, for every 1 HA that reacts and becomes product, we get 1 H and 1 A. Now let's say, for example, in this that A had a coefficient of 2, you would add 2X to that. Or if HA was 2HA, you would subtract 2X. So the coefficient is included when you subtract or add X. So what we need to do now is solve for these things for equilibrium. So at equilibrium, we're going to have 0.3 minus X, and we're going to have X as our concentration of H, and X is our concentration of A. Well, we do know that we can write an equilibrium expression for this. Remember that equilibrium expression is K equal to your products over your reactants. So H plus and A minus over HA. Well, now what I'm going to do is I'm going to plug in my value for K. I'm going to plug in my values that we found at equilibrium. And now I have an algebraic formula that I can go through and solve for X. So what we end up with is X squared over 0.3 minus X. We need to get that 0.3 minus X out of the denominator and move 0.20 over. So what we end up with is X squared plus 0.20X minus 0.0X. Now you're thinking, oh, yay, this is going to be really exciting because, yes, you do end up having to use the quadratic formula to be able to solve for this. So you plug those into a quadratic formula calculator. I'm not going to ask you to do the opposite of b plus or minus the square root of b squared minus 4acl over 2a. Not that I just know that off the top of my head. But I go through, I use the quadratic formula, I get two possible numbers. One's negative. We will never use the negative because you can't have a negative concentration. So in this, what we end up getting is 0.165 for our value for x. Well, now that I have x, I can just plug it back in and solve for equilibrium. So x is the concentration of H and the concentration of A, so it's 0.165 molar. And then the concentration of the acid itself is 0.135. So doing Rice tables is something that is very, very important to make sure that you know how to do. The key thing here is to understand what you're given initially, jot that down. Typically, you're not going to have much of your products unless it's given to you in a problem. You may see one of those a little bit later on. And then just basically follow what the formula says to get your values at equilibrium. So 0.30 minus x, H is plus 0 plus x, A is 0 plus x. Make sure you write out your equilibrium expression and then just solve algebraically. Other than that, it's pretty straightforward. There is one little trick that you can use, that if k is less than 1 times 10 to the negative third, you can actually take away the minus x in the denominator. That's really nice because then you don't end up having to use the quadratic formula to go through and solve for any of these types of problems. So furthermore, in regards to calculating equilibrium concentrations, we can actually use particle diagrams and graphs to show us when a system is at equilibrium. So if I look at the example down below or the example on the right-hand side here, the graph shows that equilibrium is achieved when the concentrations of my reactants and my products do not change. In addition to that, we can look at particle level diagrams to get a good understanding of when equilibrium is achieved. So notice in the very first diagram there on the left, we have a bunch of N2O4 and no NO2. As we continue to move along the graph that shows concentration versus time, we have some NO2, but still a lot of N2O4. If I keep going to the right, eventually we see that equilibrium is reached and achieved. So once equilibrium is achieved based on the graph, you'll have some amount of reactant and some amount of product. Keep in mind that as you continue moving further right on the graph, the number of molecules that you would see on a molecular level for each of them would not change, because remember, at equilibrium, the forward rate of the reaction is the same as the reverse rate of the reaction. That means that the concentrations of your reactants and products will not change once you've reached chemical equilibrium. So keep in mind that you can use graphs and particle diagrams to be able to demonstrate this. Furthermore, if we know the concentrations, we can actually use them to calculate the equilibrium constant. We would just need to write our equilibrium expression for this and then plug in the values for concentration or pressure once equilibrium is reached, and then we can calculate the value for K. So let's talk a little bit about Le Chatelier's principle. And Le Chatelier's principle is something that's very important in the equilibrium world. Shifts in equilibrium can be achieved and even predicted when the system at equilibrium is stressed. Well, how do we stress a system at equilibrium? Well, we can do one of a handful of things. We can add a chemical, we can remove a chemical, we can alter the pressure of a gas system, or we can change the temperature. All four of these factors cause stress on a system and therefore shifts equilibrium certain directions based on whether you're removing a reactant or product, based on the number of moles of gas, and based on whether the reaction is endothermic or exothermic. So let's take a look at some of these principles and see if we can predict what shifts would happen due to Le Chatelier's principle. So the addition of a reactant is going to cause the system to respond to make more product in order to reestablish equilibrium. Remember that when we take something out of equilibrium, Q no longer equals K, if you remember that from our previous video. As a result of that, the system is going to respond by either making more reactant or making more product to ensure that Q equals K once again. So that's why when we add reactant, we make more product. We shift that equilibrium in order to make Q equal K once again. In addition, the product, when I add a product, the system responds by making more reactant to establish equilibrium. So if I add more of one side, it's going to make more of the other side in order to reestablish chemical equilibrium. The opposite can be said when we remove something. So for example, the removal of a reactant causes the system to respond by making more reactant in order to reestablish equilibrium. Furthermore, if we remove a product from a chemical reaction, the system is going to respond by making more product in order to reestablish equilibrium. So the addition of something, we're going to shift the opposite direction, but if we remove something, we're going to shift equilibrium that direction in order to reestablish the fact that Q needs to equal K at equilibrium. So when we talk about pressure, we need to take a look at the mole values for each of these. The addition of pressure is also the same as saying the reduction of a volume. Remember, the two are inversely related. We took a look at that when we were going through combined gas laws in Unit 3. But the addition of pressure shifts the reaction towards fewer moles of gas. So if I were to add pressure to the system that we see here, there are 4 total moles of gas of nitrogen and hydrogen combined as our reactants, but only 2 moles of ammonia as our product. So when we add pressure, equilibrium is going to shift to make more product because product has fewer moles of gas. The decrease in pressure shifts the reaction towards more moles of gas. So if I decrease the pressure, especially in this system, equilibrium is going to shift to the reactant side, making more reactants in order to reestablish that Q equals K. So when we look at pressure or volume, remember the two are inversely related, we need to take a look at the total number of moles of gas on our reactant side and compare that to the total moles of gas on our product side. Once we figure that information out, we just figure out if we're shifting left or shifting right, whether we're adding pressure or decreasing the pressure. So we need to understand a little bit about Le Chatelier's principle in terms of temperature. Now, one way I go through and think about this is I think of heat just like amount, like when we added something, a reactant, or we added a product. We just need to think of heat as a reactant or product, and that's going to be dependent upon whether the reaction is endo or exothermic. Remember that in an endothermic reaction, heat goes in, so we would treat heat like a reactant. Furthermore, if we have an exothermic chemical reaction, we would end up treating heat just like a product because exothermic reactions release heat. So if we think about that, and we think heat and temperature related, as the temperature increases, so does the heat, we treat heat just like a reactant or product, whether we're adding it or losing it. So increasing temperature favors products in an endothermic reaction. So stop there for just a second. So if I take a look at the endothermic reaction on the right, it says that increasing temperature favors products. Well, if we think of heat just like a reactant and it goes up, equilibrium is going to shift to the right in order to make more product. So that makes sense. And then furthermore, increasing a temperature favors reactants in an exothermic reaction. Well, if we look at the exothermic reaction, heat's on the right-hand side. We treat it just like amount. So if heat goes up, equilibrium shifts to the left to make more reactants. And then decreasing temperature favors reactants in an endothermic reaction and products in an exothermic reaction. Again, if we just treat heat like amount, it's very easy to figure out what shifts are going to happen in an endo or exothermic chemical reaction. So let's go through and try to justify some of these shifts in chemical equilibrium due to Le Chatelier's principle. Unfortunately, I already put the answers on here, so we're just going to roll with it. So I balanced the equation. I put a 2 in front of NO2, and then I added heat as a product because delta H is negative, and negative implies an exothermic reaction, so heat's going to go on my product side. So let's think about how these are going to cause shifts in equilibrium. Well, if I add N2O4, that is adding a product. Remember that when we add a product, equilibrium responds, or the reaction shifts, in order to make more reactant. So we're going to make more reactant. When we remove NO2, we're taking away a reactant. The system is going to respond to reestablish equilibrium by making more reactant. If we increase the volume, that is, we decrease the pressure, remember the two are inversely related, decreasing pressure favors more moles. So as a result, we have 2 moles on the left side and 1 mole on the right. So we're going to have more reactant. If I decrease the temperature, remember we treat heat just like a reactant or product. So decrease the temperature, heat is going to go down. When we remove a product, we're going to make more product. So equilibrium will be reestablished with more N2O4 or more product. Adding N2, now we haven't talked about this yet, but adding something that does not participate in the chemical reaction causes no shift, no change in equilibrium at all, due to the fact that it doesn't participate in the chemical reaction itself. So what are some things that don't cause equilibrium to shift? Well, we already talked about one, the addition of an inert substance, addition of a substance that does not participate in the chemical reaction. The other thing is the addition of a catalyst. Now, I'm not saying that the catalyst does not participate in the reaction. It's a very important part of the reaction. One thing I want to make very clear is that the addition of a catalyst does not change where equilibrium is established. It just changes the speed at which you reach chemical equilibrium. Remember that catalysts speed up reactions by lowering activation energy. It does not change the value for K whatsoever. Now, changes and shifts in equilibrium can be graphed to show how equilibrium is reestablished. So in this instance here, I have the Haber process, which we've talked about quite a bit. It looks and appears as though there is an addition of hydrogen that is added at a certain time. Well, once hydrogen is added, remember that equilibrium is going to The system's going to reestablish equilibrium by making more ammonia, and you can see that. We lose some of that hydrogen after we add it. We lose some nitrogen after we add the hydrogen, and there's more NH3 as our product. So we can graph these and understand where equilibrium is reestablished. Furthermore, we can also calculate the value for K utilizing these graphs before and after. And one thing you'll notice, other than the addition of temperature, is that the value for K should stay the same. So Le Chatelier's principle really isn't an explanation or a justification. It's just a way to get an idea of what's going to happen when a system is disturbed. What I really want you to understand is that when we alter equilibrium, Q is no longer equal to K. The system then responds by making Q equal to K again, so that is where we make more reactant, we make more product, in order to justify the fact that Q is going to equal K once again. Le Chatelier's principles are not a justification. It is a way to help get us a better understanding of what does happen when equilibrium is altered, but you really need to make sure that in your response, you describe the fact that when we make these changes, Q no longer equals K. Therefore, we need to make more reactant or more product in order to ensure that Q equals K again, because when Q equals K, we are at chemical equilibrium. Temperature is the only change that actually changes the value for K. So if we think about it, if let's say we have an endothermic reaction, so heat is on my reactant side, and I increase the temperature, I make more product. Well, that would tell you that K increases, right? Because a larger value for K indicates more product production. Furthermore, if we have, let's say, we have that same endothermic reaction where heat is a reactant and we decrease the temperature. Remember that we treat heat like a reactant, so equilibrium is going to shift to the left. Well, in that case, the value for K gets smaller because we have more reactant and less product. Temperature is the only change that actually changes the value for K. Nothing else there does. It just reestablishes that Q equals K. So we've covered quite a bit of content in this particular video. One thing I want to make sure that you're very clear on is that Rice tables are something that's going to be very important in addition to Le Chatelier's principles. So this is probably one of the more important videos that you make sure that you understand and are able to go through and really get a good grasp of the content. Really appreciate your time. Thank you for watching. If you have any questions, make sure that you let me know. This is Chatelier Bio. Make sure you like, comment, and subscribe, and we will see you next time. Have a great day.